Welcome to Lecture 24A, entitled Stokes Theorem for 3D. And this is a tooling example where we basically just gain some flexibility of using Stokes Theorem, and that is to calculate the left-hand side and the right-hand side. The material for this video comes from reading Assignment 4, Section 4.2.1. And the objectives are to develop the skills for applying Stokes' theorem to purely geometrical problems. Concepts, conventions, visualization skills include closed contour encloses a surface. In this case, the surface is an open surface, right? So contour basically bounds a surface, but it's an open surface. And the direction of a surface area vector and the direction of the traversal of the contour are related to each other by the right-hand rule. As usual, the second slide is just a review of the slides to follow, so we'll just basically move on. Okay, so let's start with this example. This is Stokes tooling example. If you want to access the graphics, then the URL is mentioned on the left at the top. And the slider T in the graphics, what it does is moves the blue triangle to cover the pyramidal box. So for instance, this blue thing will move towards here and sit on top. So you can see this is almost like a top face and then three triangular inner surfaces. But this set of red lines here and this set of red lines are essentially identical to each other. Okay, so the problem statement is to evaluate the closed contour integral f dot r dot t dt, where f is z minus z x squared minus y squared. And the contour, which is shown in red, consists of three line segments that bound the plane z equals 8 minus 4x minus 2y in the first octant and oriented according to the figure below. The vertices of the triangle are at 0, 0, 8, 2, 0, 0, and 0, 4, 0. So you'll notice here that I have basically a contour. It's going in a counterclockwise direction. The contour base is not smooth, and therefore we have to partition it into three separate line segments. And according to Stokes' theorem, if you use the right-hand rule, the fingers point in the direction of traversal, and the area vector points in the direction of the thumb, which would be in this direction here. So we're going to look at this as one possible scenario. This is the area that's enclosed by the contour. But you could go back here and just look at this as being a box, right, with a triangle face on one side, another triangle face on the other side, and a third triangle face here. But basically, the rim is this contour that we see here, the same as this contour. And again, because you're going in this direction, then using the right-hand rule, the surface area vectors would have to be pointing in the direction of the thumb, which means in this direction, and in this direction. So there are two different classes of problems we want to look at. We want to show, in fact, that if we apply Stokes' theorem to this area or these three discrete surface areas, we end up with the same result. The choice of surface is somewhat arbitrary, so long as the surfaces all share the same boundary. That's a contour. So we're going to apply Stokes' theorem to solve this problem. F dot Ts, integral of a round closed loop. In parameterized form, it would look like this. And so r base would be a position vector, and r dot would be the derivative of the position vector with respect to the parameterization variable t. This we'll call the left-hand side of Stokes' theorem. And on the right side, it says that if you take the curl of the vector field, dot product with the surface area, integrate over the surface, then that's the same as if you were doing the closed contour integration. And we'll call this the right-hand side. Since we're going to do the right-hand side at some point, we might as well compute the curl of the vector field. So this is set up in a determinant form. First row are the unit vectors, the second row is the partial derivatives, and the third row are the components of the vector field. If you take this and apply to the vector field here, you'll end up with this being, the curl of f. So again, we're going to consider two simple cases, the light blue shaded area and the multi-gray shaded area, to show that any surface bounded by a common contour C, shown in red, will give the same result for the surface integral of curl of f dot n ds. So we're going to look at this case and we're going to look at this case in turn. All right, this is just showing a blow up now, so it's just a little bit more detail, easier to visualize. Consider this two simple cases, the light blue shaded area and the three triangular segments, which basically form a surface, an open surface bounded by this contour. Okay, so the bluish gray triangle area is the light blue area projected onto the XY plane. And so here again we have the contour in a counterclockwise direction, the area vector pointing in this direction. Again, right-hand rule. Here we have the same contour, but looking inside the box. Again, these area vectors are pointing in the correct direction according to the right-hand rule. All right, so let's do, for the shaded in light blue, which is the planar area, let's basically do the calculation of the right-hand side. So because the plane equation is given as a function of x and y, that is z is a function of fxy, and we need to basically determine what the differential surface area is, it's easiest is to use an explicit representation. And so in this case, the area vector has to be pointing in the z direction, and so this is the appropriate form to take. So z partial x, z partial y, both minus 1 dy dx. And so if you take the equation of the plane, take the partial respect to x and the partial respect to y, times negative, then you'll end up with this vector here, a dy dx. And the direction, as I said, is according to the right-hand convention. The region R, which is the surface over which you're going to integrate, is the triangular region R in the xy plane, which was the darkish grayish blue color, dark blue, is found by setting z equals 0 in the equation of the oriented plane. And so if we set this equal to 0, that'll give you an equation of y as a function of x, and that can be used then to determine the region. And this is what we've done here. So we have one bound, which will be y equals 0. One bound is 4 minus 2x, and x ranges between 0 and 2. This is the projected area of the plane, z equals 8 minus 4x minus 2y onto the xy plane. All right, so now that we have the region, which basically gives us the integration limits, we also have the surface area vector, and we also have the curl of the vector field. We can now basically do the calculations shown here. So here's the curl of the vector field. Here's the differential surface area. Here are the bounds on the integral. We just performed this integral, and we'll end up with an answer of minus 88 over 3. So in this case, the circulation around the boundary is negative, indicating a net circulation in the counterclockwise direction looking from above. So we just arbitrarily went around in a counterclockwise direction, but we've ended up with a negative circulation, which means the circulation is going actually in the opposite direction, which means its net is in the clockwise direction. Okay, now let's do the three discrete planes. Since we're going to basically do the curl over a surface, the surface is not smooth, but consists of three triangular segments, and so this double integral is actually the sum of three separate integrals in individual surfaces for the three different triangular surfaces, S1, S2, and S3. And so we need to basically compute for each one of these cases what is curl of F and what is going to be NDS. So for the y equals 0 plane, we take the curl of F and we set y equal to 0. And so this is the curl of F that we're going to be using as the integrand. For z equals 0, that means we set z equal to 0 in the curl of F. This is the expression we use for the integrand. And for the case x equals 0, set x equals 0 in the curl of F, and this is the expression we use for the integrand. Similarly, at y equals 0, this is the differential area. And so this is the differential area that's pointing in the y direction, which is the correct direction, according to the diagram which we've shown earlier, dx dz. This is the vector pointing in the z direction for another of the triangular elements, dy dx. And this is the third, which is in the x direction, dz dy. Notice that the vector, this space is the x, this is dz dy. So it's always going to be, whatever this is, the remaining two are the the differential elements. So these are in the correct direction. These we've now computed. And so now the only question is determine the bounds on the integrals. That's for S1, S2, and S3. And so for S1, we'll have 0 is less than equal to y is less than equal to 4 minus 2x, and 0 is less than equal to x is less than equal to 2. And so you can obtain these basically just by looking at the diagrams from the previous page. There's the individual triangles, and you just have to find the bounds. For S of 2, we have these bounds, and for S of 3, we have these bounds. Okay, so just a general note. The differential area can be determined by inspection if the area is very simple. And if that's not the case, you just compute it mathematically. So we more or less have everything ready. We can move to the next step. And so here we just collect the terms and do the integration. So the curl of f dot n s3 ds3, that's the case for y equals 0. We end up with this. For the case z equals 0, this is a different surface area element. Take the dot product, we end up with a 0 value. And for curl of f, evaluate x equals 0 for ns2 ds2, we get 1 minus 2y dz dy. And so we now basically substitute that into the three separate integrals, one here, and one here. The first one, which is the one involving S1, is 0. The involving S2 is 1 minus 2y dz dy, and the one involving S3 is 1 minus 2x dx dz. So these are the two last expressions that you see here. If you do these integrations, again, you'll end up with the answer of minus 88 over 3. So it really didn't matter what surface area we used. We end up with the same result. Okay, so now we're going to calculate the left-hand side of Stokes' theorem, see whether or not we get the same answer there as well. All right, well, the left-hand side is the closed contour integral. Right here, it's going to be in a parametrized form. Because there are three individual line segments, this closed contour is basically contribution for each one of those segments. So we're going to basically have to parameterize the segments in a different way. And again, recall that t should be advancing as you move around the contour. So for C1, the position vector, that would be this one here. R1 would be 0, 4 minus t, 2t. And so you can prove that for yourself. And t will range from 0 to 4 as you go from this point to this point. We'll also need R1 dot t, which is the derivative of this vector, which is what is required to be substituted in here. So for f, basically, we have 2t minus 2t minus 4 minus t squared. So you take the f vector, which are in terms of x and y and z, and you substitute in the parameterization values for x. So for x, we would have substituted 0. For y, we would have substituted 4 minus 2t. And for z, we would have substituted 2t. And we end up with this for the vector. Again, the components is a function of t. You can do it also now, the position vector for R2, which is going from here to here. If you basically go through that, you can show for yourself that the position vector takes on this form. T is ranging from 0 to 2. And so as you go from 0 to 2, you're basically traversing this line here. And then you need R2 dot, which would be just taking the derivative of this. And then you're able to substitute in here. Similarly, f value will basically be based on the position vector. So substituting the x, y, and z values, using the individual contributions of the x, y, and z into x, y, and z in f gives you this expression. And C3 basically is just the last one. We need a position vector that takes us from here to here. And so you'll see that if t goes from 0 to 2, we'll be sweeping out this contour here. Again, R3 dot would be just to take the derivative of this with respect to t. And then the vector field f will be basically the same thing. The x's, y, and z's get basically changed to values representing what the x, y, and z values are with respect to the functions t. All right, so now that we have the f values and we have the r dot values, we can then go ahead and basically do the computation going around the contour. And so we have three contributions, f dot r1t, f dot r2 dot dt, f dot r3 dot dt. And so all I've done here then is to take the bounds, which are given, right? I've taken the f vector, which is a given, and the r dot dt vector, which is given, and compute. So for this term, we get a contribution of minus 80 over 3. For this, we get a contribution of minus 8 over 3. And for this term, we get a contribution of 0. If we add them together, we get minus 88 over 3. Again, the same result. Okay? So, as I noted, the contour applies to both geometries as previously investigated. So we've shown that it doesn't matter which side you use. Essentially, the answer is the same, which basically just proves that Stokes theorem is actually, it works. All right, so let's do example problems and then look at the solution. I've drawn the picture on the right-hand side that you can use for reference purposes, and you can look at this link if you also wish to. We want to compute the line integral, closed contour integral, y plus sine x dx plus z squared plus cos y dy plus x cubed dz. So this is written in an explicit form. All right, this is an explicit form. Also, we're given that the contour is the curve r of t is sine t cos t sine 2t, and 0 at t goes from 0 to 2 pi. And this line lies on the surface defined by z equals 2xy. Okay, so if we just look at these expressions, the first observation is that any form of closed line integral can be associated with Stokes theorem. So we know we're going to use Stokes theorem. Observation 2, that any surface bounded by a closed contour can be associated with Stokes theorem. Right? So the fact that we have a surface that's bounded by a contour means we can invoke Stokes theorem. So we're going to apply Stokes theorem. And again, this is what it looks like. This is a sort of general form in which we have it, but this is what we use for calculation purposes. So this is the left-hand side, this is the right-hand side. So the general question you might ask yourself is, which is the easier to compute, the left-hand side or the right-hand side? It'll be case by case, and generally speaking, you'll want to basically take the simplest possible approach unless someone asks you to do it in a specific way. So the first step is to determine the orientation of the curve. And so you have to go to the position vector, and you basically go from t0 to t2 pi and trace out the path that's taking place. It turns out the path is moving like this around the contour. So looking downwards, it looks like it's going in a clockwise direction. So using the right-hand rule, that means you would have to take your fingers and point them in the direction of traversal, which will be in the clockwise direction. Okay, so that's the statement that's made here. All right, so let's do the calculation. If we were to write out the left-hand side of Stokes theorem, okay, which would be this part here, you'd start with dx equals dx dt dt, dy equals dy dt dt, and dz equals dz dt dt. And recall from a previous lecture that TDS is just dr dt dt. This is the vector, the position vector. All right, and this would be just like writing this out in full form, dx dt, dy dt, dz dt. Right, and this we would call r dot dt. But if you multiply through, this is also equivalent to dx dy dz. So this is the explicit representation. This is a parameterized representation. So that means we could write this expression that we were given as basically this in explicit form times, or at least dot product with dx dy dz. And so from this it's clear that the f vector is y plus sine x, z squared plus cos y, x cubed. All right, so this expression that we're looking at looks messy. All right, so right away we're going to make the call. I don't think I want to go that way. So instead we're going to explore the right-hand side of Stokes theorem for calculation process. So what are we going to need to do? We're going to have to determine what the curl is. We're going to have to determine the orientation of the surface area vector. We also determine what surface area to use, because it's really up to us to choose the surface area. And so there are a number of options here. Two things have to calculate, but we also have to detect what the surface shape should look like. Okay, so if we're looking down on the xy plane, the contour is traversed in a clockwise direction. Therefore, the right-hand conventions would stipulate that the area vector NDS has a z component which points in the minus z hat direction. You could see that on the previous picture that the surface area vector was pointing in the minus z hat direction. The surface z equals fxy equals 2xy is given in explicit form, so the surface area vector pointing downwards can be expressed in explicit form. That means you can just write it out as such. So this is f partial x, f partial y minus 1. So this is the correct direction. So we just have to basically do the computation of the partials of x and y, and that's what we've done. Here it is, 2x, 2y minus 1, and dy dx. If you take the curl of f, you'll end up with this expression. but we need to evaluate the vector on the surface, which is when z is equals to 2xy. So wherever we see z in the original vector function, in the curl of the vector function, the z now gets replaced by 2xy. So this z now becomes 2xy, making this minus 4xy. These two terms are unchanged. Why? Because they're not functions of z. All right, so we can basically put the pieces together, the curl of f and ds. Here's the curl evaluated on the surface. This is the differential surface area. And so now we basically have to establish what the integration bounds are going to be. So that's the next step that's shown here. So the bounds for the region of integration are determined by the projection of the contour onto the xy plane. The bounds can be determined by taking the original position vector and setting the z component of the vectors as 0. So we had a term in here. We're just going to set it to 0. And so this is two-dimensional now. Again, 0, t would be going from 0 to 2 pi. And so this is the position vector that traces out the contour, which bounds the region over which we're going to integrate. And it's a circle of radius 1 on the xy plane, and it's shaded in gray here. So the domain for integration for S will be in Cartesian coordinates. The upper semicircle is square root 1 minus x squared, lower semicircle minus square root 1 minus x squared, and the integration limits on x are minus 1 to x. So here are the bounds for the inner integral, and these are the bounds for the outer integral. All right, so now we basically just put it together. Here are the bounds. Here's the resultant of the dot product, and so now we integrate this. Of course, we look at it and say there might be an easier way to integrate it. This looks like a problem in which we could use polar coordinates. Recall, in polar coordinates, x is r cos theta, and y equals r sine theta, and dy dx becomes r dr d theta. So we just transform the integral so that this now just becomes the radius from 0 to 1, and we go once around the circle from 0 to 2 pi. And we make the substitution for x from here, the substitution for y from here, put it together, and we end up with this expression. After integrating with respect to r, we end up with this expression, and the last step is to integrate with respect to theta. So finally, we end up with an answer of pi. If you work through this, you'll have to use some trigonometric identities to get into a form which is suitable, but the final answer in this case is pi. That concludes Lecture 24A. Thank you for listening.